Acoustical control in buildings. Sound is energy, and like all energy, it radiates outward from a source. It moves the same way that heat energy and light energy do by traveling through air, solids, and other materials. While there are many beneficial sounds that we want to hear as they travel through space, such as speech in a classroom or music at a concert, there are other sounds that we don't want to hear, which we call noise. This unwanted or interfering sound in building spaces can come from a variety of sources, both within and outside of a building, such as outdoor traffic, activity in an adjacent room, or mechanical equipment. A certain amount of background noise is certainly commonplace and even acceptable. However, excessive background noise can seriously degrade the ability of people to communicate, overshadow preferred sounds, or prevent audible signals from being heard. The scientific study of sound and noise has not only looked at the physics of sound, but evolved into a field of acoustics which looked at sound in all its forms. Architectural acoustics in particular is specifically related to the interactions of sound both within and between architectural spaces and the impacts on people in those spaces. As such, a significant body of knowledge is available on how to deal with sound in human environments as part of the field we know as acoustic design.
Sound generation. Sound can be generated from single or multiple sources but is typically characterized by three characteristics. Frequency, pitch. Wavelength. Amplitude, loudness. Sound is characterized by its frequency, pitch, wavelength, and amplitude, volume. Sound waves can travel through any media, such as air, water, wood, masonry, metal, etc. Depending on the media through which it travels, sound is either considered airborne or structure-borne. In most noise control situations, both airborne and structure-borne sound must be considered. Sound transmission. The following is a summary of terms and measures relating to principles of controlling sound transmission between spaces. Transmission loss TL. Sound transmission class STC. Outdoor-indoor transmission class OITC. Impact insulation class IIC. Ceiling attenuation class CAC. Transmission loss. Sound transmission class. Sound transmission class STC is a measure of airborne sound transmission loss, while the impact insulation class IIC is a measure of structure-borne sound transmission loss. Outdoor-indoor transmission class. Impact insulation class. Ceiling attenuation class.
Sound and indoor environmental quality. With an understanding of the principles of sound generation and sound transmission, we can focus on the impact of sound and noise on the indoor environment. When unwanted background noise has interfered with normal activities in a space, our tendency, if we are talking, is typically to speak louder. In fact, it is generally accepted that most people would need to speak at least 15 decibels louder than the background noise level in order to be heard at all. This observation and others has led to the development of national standards such as ANSI Standard S12.60 or the Acoustical Performance Criteria, Design Requirements, and Guidelines for Schools. Educational settings under this standard, single or composite wall assemblies should provide STC ratings whenever separating a core learning space, for example a classroom, from a specific adjacent spaces as follows. Since classrooms can also be above or below each other, ANSI Standard S12.60 also identifies specific impact insulation class or IIC ratings and recommendations for classroom learning spaces, including the following. Green building codes such as the International Green Construction Code or IGCC and the California Green Building Standard or CalGreen similarly address acoustic control in all types of buildings. Many of these standards and requirements are responding to independent research conducted in a variety of university and clinical settings to determine the relative effects of noise on people in indoor environments. The findings have been convincing enough to determine that background noise can contribute to poorer performance in schools, longer patient recovery times in healthcare settings, and detrimental health effects to employees in any setting. As a matter of public health, safety, and welfare, then, acoustic is increasingly being viewed as a significant component.
In this part, I will discuss about the sound mitigation in ceilings to floor. So, simple as mitigating sound transfer between two floors through design, details, and insulating materials. In this case, you need to consider the type of noise, if it is an airborne or an impact noise. Noises from airborne sound occurs when sound transfers directly from a source to the receiver. So, an airborne noises are commonly came from a TV noise, from shouting of the children or the residents, music, and others. Secondly, noises from an impact sound are those noise is structural vibration transmitted from a point of impact through structure. It is commonly caused by an item hitting the floor, dropping items on the floor, children running or jumping, and others. The question here is how to build or how to have a soundproof ceiling. In multi-story building, the ceilings are also a floor from the story above. Here, use acoustic insulation inside your voice to reduce airborne sound. Whether you are insulating existing ceilings or soundproofing a new build, use acoustic insulation slabs between the joints to achieve the required levels of noise reduction. And I want to remind everyone that do not use thermal insulation rolls for this, as they are low in density, which means they will not block and absorb the airborne sounds. Instead, you can install DFM acoustic insulation slabs inside the ceiling cavity. These slabs are compressed to increase the density of the insulation, making them suitable for using as acoustic infill between the joints. DFM insulation slabs are supplied in 1200 mm by 600 mm slabs, and they range in density from 45 kilograms by cubic meter up to 140 kilograms cubic meter. Acoustic slabs are supplied in 25 mm, 50 mm, 75 mm, and 100 mm thickness. In this case, building regulations stipulate that the insulation used between separating floors should be 100 mm thick and have a density of 45 kg per cubic meter. Although using the density of acoustic insulation will help you meet that required Part E levels, we would recommend using higher density for most domestic soundproof solutions. Compliance with regulation does not mean that sound will not transfer between rooms. For a higher level of sound insulation between rooms, use the 100 mm by 80 kg per cubic meter DFM slab. The higher the density, the better the sound insulation performance. The level of improvement does diminish with each increase in density. We recommend the 80 kg per cubic meter as it offers good levels of airborne sound insulation compared to the money you spend. Double the density does not equal the double performance, but it will double the cost. Use acoustic hangers and create separation in the ceiling structure. As a part of soundproof solution, creating separation in the construction is vital to increase airborne and impact sound insulation. Build an independent structure below the existing ceiling for the best solution. This type of construction can only be carried out if you have enough height in the room. The ceiling height will drop by approximately 6 inches. Use an acoustic hanger to create the separation if you cannot afford to lose this much height. Attach sound breaker bars to the underside of the joints at around 350 to 400 mm centers. Hang acoustic plasterboard from the bars to reduce sound transmitting through the ceiling structure. Sound breaking bars will reduce sound transferring through ceilings. Sound breaking bars are an acoustic hanger designed to be attached to the underside of the ceiling's joints. The unique design of the sound breaking bars reduces sound transmission through the ceiling structure, reducing impact and airborne sounds. Most new build and conversion projects use this type of acoustic hanger as part of the new separation construction. Plasterboard can be fixed directly onto the bars rather than into the joints. The bars separate the board from the joints and reduce surface area contact. They also absorb vibration, reducing airborne and impact sounds transfer. Use soundproof panels to block airborne noise. A quick and simple method of soundproofing a ceiling is to increase the mass of the ceiling. If you do not want to remove the plasterboard or you can't Use a soundproof panel fixed below the existing structure to stop the sound from TVs and conversations. Use the noise stop acoustic panel, your existing ceiling, to block normal domestic sounds from transferring in the room. Simply screw through the existing board into the joints, seal the edges with an acoustic sealant, plaster, and decorate. These panels will reduce more noise than standard acoustic plasterboard due to the acoustic layer on the back of the panels, which increase the mass of the boards and reduces vibration through the panels. This means less noise will pass through the panel into the room. A normal ceiling construction to comply with the current regulations would include the following materials. First is acoustic insulation, 100mm by 45kg per cubic meter. Sound breaking bars, 12.5mm acoustic plasterboard, 2 layers. In order to comply with Regulation Part E, you will have to pass a sound test which will include an airborne test and an impact test.
Sound control in mechanical systems. HVAC equipment for a building is one of the major sources of interior noise, and its effect on the acoustical environment is important. Further, noise from equipment located outdoors often propagates to the community. Components of the mechanical system, for example, are fans, dampers, diffusers, and dump junctions, all may produce sound by the nature of the airflow through and around them. As a result, almost all HVAC components must be considered as well as for its effects for the whole building. In the majority of rooms or open spaces, the most common source of disturbing noise is the HVAC noise, or the equipment that is for heating, ventilation, and air conditioning. The primary objective for acoustical design of HVAC systems and equipments is to ensure that the acoustical environment in a given space is not unacceptably affected by HVAC system-related noise or vibration. Noise points in HVAC system. Sound and vibration are created by a source and are transmitted along one or more paths and reach a receiver, just like what the picture shows. System analysis for noise control uses the source, path, receiver concept, and the source of the sound is the noise generating mechanism. The picture shows how the sound travels from the source via a path which can be through the air or airborne or through the structure called as structure-borne or a combination of both paths until it reaches the receiver, which is the building occupants or outdoor neighbor. The design of ducted HVAC systems must address 5 distinct but related issues, which are the mechanical system noise components. It is important to know which of these paths is most likely to cause acoustical problems so that it can be dealt within the design phase of the project. Treatments and modifications can be applied to any or all of these elements to reduce unwanted noise and vibration, although it is usually most effective and least expensive to reduce noise at the source. The next is about the typical mechanical system's noise components. Number 1. Duct-borne noise. It is generated by the flow of air and is directly dependent on the velocity of air. It is called as regenerated noise, which propagates along the ductwork, follows all transitions and takeoffs, and ultimately exits at the diffuser or grill. Number 2. Radiated equipment noise. Generated by vibration of the mechanical equipment such as pump, compressor, air handler, fan and motor, and is transmitted through the wall or flow into the adjacent space. Number 3 and 4. Duct break-in and breakout noise. Duct breakout noise transmit through the wall of the duct, thus impacting the adjacent space, while the duct break-in noise is radiated equipment noise that enters the ductwork and propagates down the duct system. Flexible ducts are
especially prone to break-in noise because of lightweight. And lastly, number 5, terminal noise. The final links in the air distribution chain are the terminal air devices. These are the grills, diffusers, registers, and vent covers that go over the duct opening in the room. When selecting terminal devices, always select a device that has noise criteria rating of NC 30 or lower for the designed airflow rate. What do we do in order to reduce the noise from HVAC equipment? And there are 4 ways to do it. First way is to follow the guideline of lower and slower. Lower volumes of air moving through the system with fans and blowers operating at a slower speed will lower the source of the noise. Another tip to reduce the noise from HVAC equipment is that the central air equipment should also be acoustically isolated from spaces where airborne noise would be objectionable. Then, the equipment should also be mounted on vibration isolators to avoid transmission of structure-borne noise. And last from the list is that sound traps or buffers will help to attenuate equipment noise in adjacent ductwork. And next we have the noise control strategy for HVAC systems that can be described by the following 8 steps. Majority of the noise in HVAC systems is attributed to the air distribution and the fan systems. So number 1 is to select a suitable location for mechanical equipment, rooms away from noise-sensitive areas of the building. Number 2, select fans with low sound power output levels. Number 3, vibrationally isolate the fan. Number 4, acoustically isolate the fan noise. And the remaining 4 noise control strategy for HVAC systems are: number 5, calculate the attenuation of the sound propagating through the duct system so that the sound power entering each room is known. We have another, number 6, estimate flow noise sound power levels entering each room. Then, number 7, calculate the combined sound power entering the room and the expected octave band sound pressure levels in each room. And lastly, number 8, if the desired noise criteria are exceeded, further reductions are needed.